So we can, please go ahead.
You can see my screen, right?
Yes, we can see your screen. It's not in full screen though. Maybe you can go.
Maybe go to full screen. Huh?
Yeah,
Oh,
yes.
it's already full screen.
Now, maybe there was a delay, but now it is in my screen.
Yeah.
Okay.
I normally use the white screen for your slides. You can choose that.
Oh, yes. Okay. So, good afternoon, everyone. So I first like to thank Zhongbo for the invitation. And I used to spend 2 years as a visiting student in Berkeley Lab, where I learned a lot of stuff by working with Xinian first and later on with Feng. So that was the real start of my academic career. So, besides, I also miss seeing the sunset on the Golden Gate Bridge on my way home from work. So it was really nice, pleasant 2 years stay in Berkeley. So today I'm very happy to have the opportunity to discuss our recent work on UPC physics. In this talk, I will pay particular focus on the spin-dependent effect. The work I'm going to discuss have been carried out with many collaborators. Okay, this is the outline. I will start with a brief introduction to the studies of UPC physics and explain why people are interested in studying UPC process. I also talk about the recent discovery of the linear polarized coherent photons. Then I will talk about some diffractive vector measure production in UPCs. The most intriguing effect involved in diffractive production in UPC is a double slit interference effect, which will be explained in details. In the third part, I will discuss the Azimuthal asymmetries in Rho-zero production and what can we learn from these asymmetries. So first of all, what's the UPC? In UPC, two nuclei interact electromagnetically rather than hadronically by physically missing each other. The EM field of the fast-moving charged particle can be treated as a flux of the quasi-real photons moving along the same direction. This is often referred to as the equivalent photon approximation, or the Isaac-Williams method. When the wavelength of the quasi-real photon is comparable with the radius of the Hadron Ion, the classical electromagnetic field is coherently generated by all charge inside nuclei. So strength of the field is proportional to the nuclear charge number. Correspondingly, the number density of coherent photon is proportional to Z square. The photon-photon interaction cross-section in Hadron Ion clear is therefore enhanced by a factor Z2 force as compared to that in PP clear. Another type interaction, photon-nuclear interaction. Another type interaction is the photon-nuclear interaction. That can also occur in the UPC. Okay, so in the context of TMD factorization, the matrix element definition of photon TMD is given here. F is the electromagnetic field strength operator. Here we have two open transverse indices here, mu and nu. The tensor structure can be parameterized into two terms. Keepable is photon transverse momentum. The coefficient associated with the first structure is the unpolarized photon distribution. The second one is the linear polarized photon distribution. So this is a definition of the electromagnetic field strength operator. By taking partial derivative, it can be converted into this form. This keepable mu is photons transverse momentum. K plus is longitudinal momentum. So at small x, well, K plus component is very small. Then we can simply neglect the first term. So we are left with only the second term. So now it becomes clear that the polarization of the photon should be proportional to its transverse momentum at small x. This implies that the unpolarized, because this structure, tensor structure must be proportional to keep over mu and keep over nu. So this implies that these two structures should cancel out. This implies that the unpolarized and linear photon TMDs are identical at the small x. So for exclusive process, a photon TMD, it can be computed in terms of a charge form factor. For exclusive or semi-inclusive process, of course, the photon TMD takes a much complicated form. Okay, so in our this actually the linear polarization of gauge bosons at small x is quite a common feature. So in our early work, we also discovered that small x gluons inside the unpolarized nuclei are also linear polarized. Okay. Then through a tree-level QED calculation, one finds that a linear polarized photon can generate a cosine 4 phi as mass modulation in dielectron production cross-section. Here phi is defined as mass angle between y individual electrons transverse momentum and the total transverse momentum of lepton pair. That's how the delta phi is defined here. Of course, here we consider the back-to-back limit, where P-pop is much larger than total pair transverse momentum. So then we went on and carried out some calculation. Then we found the quite sizable cosine 4 phi asymmetry. So our prediction was soon confirmed by star measurement. Let me show the numerical results directly. In this table, we compare our calculation with star measurement. So one can see that our QED prediction matches the experimental results very well for UPC case. It's very close to the measured asymmetry. As for the peripheral clearance, so our results slightly overshoot the star measurement. So I suspect the reason why there's some small discrepancy is because that in our theoretical calculation, we only taking into account pure electromagnetic lepton production, while some amount of lepton pairs are from hadronic background in peripheral clearance. So if I remove this part of the contribution in the denominator in the data analysis, it may make the measured symmetry a bit larger. Then
can I ask? Oh
yes.
Can I ask? Is this linear polarization is a sort of intrinsic feature of any kind of quasi-William field itself?
At small x, I think so, yes.
Yeah. Well, I mean, most of the quasi-William field are small x, I think.
Yes, yes. Right. I tend to believe that's quite a common feature.
So in this case, it's true for quasi-William field for electromagnetic. It should also be true for strong interaction, right?
Yes, yes. For gluons,
that's why you see that. That's why you said the CGC type of is also linear polarized.
Right, right. Also small x gluons. Yes.
Okay, thank you.
But if I may, it's a little bit different for CGC, right? Because saturation suppresses linearly polarized.
Yes, yes. So for the electromagnetic case, linear polarization photon is accentuate the positivity bound. But for the CGC case, you have to take into account the saturation, namely the Gluon multiple rescattering effect. This will make the polarization smaller. Okay.
That's also in your paper, Jian. For the dipole grounded spin, it's also 100% linear polarized.
Yes.
For
yes,
whether
yes.
linear ground spin, indeed, there's some suppression.
Right.
You forgot your own paper.
No. I remember this. I just didn't mention this details. Yes. So let's make
if I extrapolate this, then if you consider the gluon fusion inside, like in CCC picture, if you think about the gluon fusion into some kind of diquark production, that should also have some kind of cosine 4-phi modulation. Is that correct?
Of course, I wrote a paper about this. Yes, that's why I did this calculation. It's just I basically didn't do any new calculation. I just take I just simplify the old result for heavy quark pair production, and then I got the result. So it's a pretty simple calculation. Yeah.
So sorry, I have a question here. Is it cosine 4-phi because you're looking at the diffractive process? I'm a little bit confused because usually when you have a linearly polarized distribution, it gives rise to cosine 2-phi. So I'm a bit confused. Where does the cosine 4-phi come from?
Cosine 4-phi. Okay, I will keep this in your mind. I will mention this later. Okay, I will give you into the picture value of the cosine 4-phi.
Thank you.
I will come back to this. Okay, so anyway, so it's confirmed by the star measurement.
This is respect to what the cosine 2-phi angle.
There's two lines in the direction.
So the linear polarized,
okay.
The linear polarized coherent photon plays an important role in generating azimuthal symmetry vector meson production as well. But before explain physics behind this various azimuthal symmetries, let us first discuss the very interesting effect involved in the diffractive produced production in UPCs, namely the two sources alike interference effect. So the production mechanism is schematic in this figure. The coherent photon flux into quark and antiquark pair long before hitting the incoming nuclei. Quark and antiquark pair subsequently scattering of the CGC and then recombine to form a vector meson. One should notice that the vector meson can be produced only if the coherent photon directly hits the transverse plane due to the fact that the strong interaction is a short distance interaction. The calculation of the diffractive vector meson photon propagation was formulated in the dipole model a long time ago. Scattering amplitude consists of the three parts, and the quasi-real photon wave function dipole scattering amplitude, which is related to the Coulomb distribution. The vector meson wave function. For coherent scattering, one should sum up dipole scattering amplitude for each nucleon inside nuclei before squaring the total amplitude. But in UPCs, there are two incoming nuclei. Vector meson can be produced in the transverse plane of either of them. It's not possible to distinguish these two possibilities from the observed final state products. So in principle, one should add up the amplitudes of these two production amplitude before squaring them. So this mechanism create a famous scale, the double slit. That's actually a double round hole interference setup. Such interference effect was first realized by Spencer Klein and his collaborator more than 20 years ago. As a comparison, at EIC, there is no such interference effect because there are only one nuclear target, incoming nuclear target. So to correctly account for this impact parameter dependence and two-source interference effect, one has to first formulate the calculation in the transverse position space. So let's two nuclei, colliding nuclei A and B. This is a head-on view. We assume that the room meson is locally produced in the transverse plane one of nuclei. This should be a good approximation as the Compton wavelength Zhou is much smaller than nuclear radius. So the production amplitude for Zhou produced at the position B purple is proportional to the gluon density inside the nuclei A at the position B purple, and the production also proportional to the gauge potential created by nuclei B at the position B purple. Of course, the production amplitude also depends on rapidity. Until B purple is the distance between the center of two colliding nuclei. And B purple is where Rho is produced. So the amplitude can be schematically written in this form. This is the gauge potential, this is the dipole amplitude or the gluon density. Okay. Then nuclei A and B, as mentioned, take turns to act as a target and called real photon source. These two possibilities cannot be distinguished from final state. So they should be summed. So then we have two terms in the amplitude, production amplitude. Then we should, as mentioned, should be summed. They should be summed on. Okay, they should be summed on amplitude level rather than the cross-section level. Now we making Fourier transform in terms of B purple, not in terms of the B purple tilt here. B purple tilt is fixed here, but we make Fourier transform in terms of B purple. And B purple here and the Q purple, the transverse momentum vector method are true conjugated variable. It's not possible to determine these two physics quantities simultaneously according to the uncertainty principle. But B purple tilt is not conjugated variable with respect to Q purple, the vector method transverse momentum. They are not related. So after making a Fourier transform, two natural phase emerges here. So actually the impact parameter dependence in our formula just enters through this phase. Then square this amplitude, we arrive at this cross-section formula. The first line is the incoherent contribution. Note that the transverse momentum carried by, or this is the gauge potential, okay? A represents gauge potential. Oh no, that's F represents the electromagnetic field gauge potential. And A is represent this contains a lot of contributions, like photon wave function, dipole amplitude, and the vector meson wave function, etc. So since we keep the B purple tilt fixed here, then the photon, the transverse momentum carried by this coherent photons in the amplitude and in the conjugate amplitude are no longer the same. So this is quite the bizarre feature in this calculation. Okay, then, so you can see that all this interference effect comes through this nontrivial phase factor here. One point I like that mention is that this is not the photon TMD. Instead, is photon number density amplitude. The square of the F can be related to the photon TMD here. Okay. Before presenting our numerical result, let me introduce some model inputs we used. First of all, for the Coulomb distribution or the dipole amplitude, we use the value GBW parameterization. We compute the gauge potential with the standard Wood-Saxon charge distribution to determine the impact parameter dependent Coulomb distribution. We use the modified Wood-Saxon distribution with a slightly larger nuclear radius. I think that this treatment is more or less justified because of the value neutron skin effect and pion cloud effects. So the nuclear radius of the strong interaction method should be slightly larger than its charge radius. For the vector meson wave function, we take it from this article. It fits to Hereditary wave well. Photon wave function is computed in QED, photo dependence. Some measurements measure the Zhou production cross-section together with double electromagnetic excitation in both ions. So neutrons emitted at forward angle by the fragmenting nuclei are measured and used as the UPC trigger. So in order to incorporate this experimental conditions in the theoretical calculation, one can define a tagged UPC cross-section. So well P pop tilde describes the probability of emitting neutron from the scattered nuclei at a given transverse separation. Okay, now let me show some numerical results. So this is for unpriced cross-section for diffractive zero production. Our calculation almost perfectly matches star data here. The diffractive pattern yield from a target with a blacklist limit being taken is shown on the right hand side of the plot for the comparison. So the double slit interference value lead to this deep structure at very low transverse momentum. So the double interference effect gives the destructive interference effect at very low transverse momentum at middle rapidity. Okay, so this is for we will assume here there's only one incoming nuclei, so the double slit interference effect is absent here. One also can see that this valley structure is smelt out by taking into account a finite coherent photon transverse momentum. Okay, now let's turn to discuss the gypside production.
So I have a quick question.
Yes.
What sets the hardest scale for this joint TMD factorization, joint impact?
Unfortunately, there's no hard scale. So that's why then we consider this a gypside production later on.
Right. So
yeah.
Do these results, are they sensitive to non-perturbatively large dipoles? Have you checked?
Yes. It's so we use this model input taken from this paper. So all this model, all parameters in the model is fitted to higher data. So, okay.
Can I ask a question on this plot?
Yes.
So on the left, how did you account for experimental resolution?
You mean the experimental resolution? What do you mean?
Resolution on what? On
The measurement, the experimental measurements are not perfect. And I'll say, on the right, we've been doing a bunch of work for EPIC, and, we don't see anything like those dips. And in many ways, that's a better detector than STAR.
We didn't take into this detector effects here. This smell is solely caused by the finite coherent photon transverse momentum.
Right.
Probably
So
will be further smelled out, but if one takes into account this detector effect, I don't know.
Okay, thanks.
Okay. So yeah. So for zero production, there's no hard scale. So to better justify the perturbative calculation, we better to compute the diffractive chip size production. For which case, finite state soft photon radiation effect becomes important. This is because a large log is enhanced by two well-separated scales. This chip size mass versus electron mass. For rho zero production, this is rho zero mass, this is pi mass. So the two scales are not widely separated. So they make this QED recorrections not so important. So while more photons can be emitted from lepton pair produced by the decay of chip size, this is a QED correction. If one integrates over all phase space of radiated photon, the total contribution to the decay rate of the chip size is order 1% level. However, if one look at the more semi-inclusive observer, like the chip size transverse momentum distribution, it could lead to the sizable contribution. So leading power contribution comes from the infrared region, where momentum carried by the radiated photon is small. So the leading contribution actually comes from this type of large Lagrange term. The observed transverse momentum of lepton pair is sum of the chip size transverse momentum and the recorded transverse momentum caused by the emitted soft photon. So we know that the fine coupling constant is a small number. However, it's because it's associated with this large number. So the high order QED correction is greatly enhanced by this large number. Soft photon contribution can be readily resummed to all those following the standard resummation procedure. Here the result. This is a Stuck effect. I didn't show the explicit formula for this. Yep. Okay. There was one point I like to stress again that if we integrate out the whole phase space, then the virtual correction will completely cancel out the real correction. So this QED correction will not affect the total production rate much, but it could significantly alter the transverse momentum distribution of produced chip size. Okay. So these are our results for the Azimuthal average diffractive chip size production in UPCs. This is for RIC energy, this is for LHC energy. RIC one is shown, okay. So red solid light are the 4 results. The dashed black lights represent result without including the soft photon radiation effect. Once again, the deep structure at a very low QT is observed due to this two-source interaction effect. Okay, so one also can see that the diffractive valley becomes more flat in this case. This is due to the final state soft photon radiation effect. Moreover, it's clear to see that the soft photon contribution dominates over the primordial distribution determined by the nuclear geometry at large QT. So if one wants to use this spectrum to reconstruct the nuclear geometry, then it's crucial to take into account all these effects. Okay. Yeah. Now let's move on to discuss some polarization dependent case. So as I discussed earlier, the coherent photons are linearly poised and can be viewed as a superposition state of the 2 helices eigenstate. The polarization information is preserved after dipole scattering. So this is sometimes referred to as the S-channel helicity conservation. This is essentially the consequence of the Eichner approximation. The dominant decay channel for root zero decay is pi plus and pi minus. So on left side of the card, okay. So this incoming coherent photon carries 1 unit spin angular momentum. So on the left side of the card, this dipole system carries 1 unit orbital angular momentum. And on the right-hand side of the card, the dipine system carries a -1 unit orbital angular momentum. So then the interference between these 2 p wave yield the cosine 2 phi as a master asymmetry. The here phi is still defined the similar way. It's angle between the root zero's transverse momentum and the individual pi's transverse momentum. So from this intuitive picture, one can easily understand why there's cosine 4 phi as a master asymmetry in dilepton production. That's because we have 2 incoming coherent photons. Suppose on the left side, we have 2 incoming photons carrying, both carrying +1 unit spin angular momentum. In the conjugate amplitude, both incoming photons carrying the -1 unit spin angular momentum. So then it's naturally lead to cosine 4 phi as master asymmetry in the final states. Okay, so anyway, from this analysis, one can see the linear polarization of coherent photon is a necessary condition to yield Lamb vanishing cosine 2 phi asymmetry. The merit of symmetry is displayed as function of Q perp is root zero transverse momentum in this plot. So the most distinguished feature of QT dependent asymmetry is its clear diffractive pattern with 2 maxima and 1 millimole visible. So without considering two-source interference effect, there will be only 1 peak here. Okay. Now we tend to discuss cosine 5 and cosine 3 phi as a master asymmetry. Most time are produced from the root decay in UPCs, but there are still small portion of time are directly produced. The direct pi pair production is characterized by rather flat invert mass distribution. One of the possible mechanism for direct pi pair is through this electromagnetic production by two photon fusion process. Despite the Z-square enhancement, the electromagnetic amplitude in general is much smaller than the hadronic amplitude, except for the very low transverse momentum region. This is because the Coulomb interaction is a long-distance interaction. So it scales at 1/t at very low transverse momentum. It increases dramatically towards small q pop. While QCD interaction and low q pop is described by the form factor, which is rather flat at t equal to 0. So these two type interaction become comparable at the sufficiently low QT. Here we are interested in the interference contribution between electromagnetic and the QCD amplitude. Such interference contribution will give rise to a unique cosine phi and cosine 3 phi and some other symmetry. Still, the online mechanism can be intuitively understood this way. Okay, I will repeat this. I think this cartoon is clear enough. So since we focus on the very low mass region, we deal with very soft photons. The pi can be effectively treated as a point-like particle. This is a finite cross-section from the interference contribution. One interesting observation is that this interference cross-section vanished once integrating out phi angle. So Coulomb nuclear interference does not contribute to the total cross-section. You only produce the cosine phi and cosine 3 phi modulations. So what can we learn from this measurement of cosine phi and cosine 3 phi and some other symmetry? To be short, it can help us to pin down the hadronic contribution to the mu anomalous magnetic moment. So one of the biggest theoretical uncertainty in computing the anomalous magnetic moment is a light by light scattering process. Light by light scattering can be mediated by a pi loop here. Such process can be related to the diamond pi production by two photon fusion process by the optical theorem. The existing experiment data for diamond pi electromagnetic production is shown on this plot. One can see that there's no much constraint around the Rho resonance peak. So this is precise region where we can look into in UPC process at RIC. So this is a numerical result. On the left panel, we plot the symmetry as a function of Q pop, the Rho zero transverse momentum. It's shown that the symmetry is quite sizable at very low Q pop, and then decrease with increase in pure transverse momentum. The symmetry as a function of uranium mass is displayed in the right plot. Is integrated over QT region from 0 to 15 MeV. The symmetry are sizable at low uranium mass region and gradually become negligible when uranium mass is above 1 GeV. So the symmetry present here is also actually very sensitive to the phase of the dipole amplitude. For example, if the phase is minus I instead of I, the symmetry will flip sign. So if there is some non-vanishing real part of the environment mass dependent behavior, symmetry will change dramatically. So we also would like to propose to use this observer to constrain the phase of the dipole amplitude. Okay, now let me address the last topic, cosine 4 phi asymmetry in Rho zero production. As just mentioned, most diamond pi are produced from the Rho decay, but still there's some portion of the pi are directly produced, either hadronically or electromagnetically. So in this plot, on the left side of diamond pi are directly produced by exchanging two gluons with the target. If these two exchanged gluons could effectively carry 2 units of the angular momentum, then they can yield the cosine 4 phi azimuthal symmetry in dipole system. Okay. So actually, this cosine 4 phi azimuthal symmetry has been measured by the star collaboration. So it's quite sizable here. So how can a color neutral exchange effectively carry 2 units of the angular momentum? In small x language, such color neutral exchange is known as the elliptic Gluon regular distribution. So here, this is how the elliptic distribution is defined. So this is the Fourier transform of Lamford dipole amplitude, which is also referred to as a generalized transverse momentum distribution. Depending on the different vector structure, it can be parameterized into these terms. This is the norm-unprized Lamford dipole distribution, and this is a spin independent ordinal. This is just the elliptical Gluon distribution. Elliptic Gluon GTMD. So it effectively carries the 2 units of the angular momentum here. So in recent years, actually, it has attracted a lot of attentions. And normally, people propose to measure this through the diffractive dye-jet production in UPC or in DIS. Okay, so now we made some numeric estimates here. Note that the final state soft photon radiation can also give rise to a cosine 4 phi asymmetry. In the upper right plot, we show the symmetry for dipole produced in UPCs from different sources here. One can say that the QED here contribution alone is not adequate to describe the star data. This is for elliptical Gluon distribution. Of course, we currently know nothing about the elliptical Gluon distribution, so we use some model input. We basically make the elliptical Gluon distribution as not as large as possible. Yeah, but still we cannot get much symmetry out from the elliptical Gluon distribution. The total contribution is still lower than the mirror symmetry here. Okay, the cosine 4 phi asymmetry for directive dipole production in EIC is displayed in the lower left plot. The contribution from the elliptical Gluon distribution into a symmetry flips the sign as a result of the absence of the double slit interference effect in EA clearance. So as I just mentioned, the convention way proposed in the literature to probe the elliptical Gluon distribution is through the cosine to find asymmetry in diffractive dye-jet production. But what we proposed here is much a clean observer to probe the Gluon regular distribution at EIC because it's free from the contamination from the final state soft Gluon radiation effect in the diffractive dye-jet production. Now let me close this part discussing with a final remark. For vector meron photon production, there's no, actually for ρ0 photon production, there's no hard scale. The transition from the quark-antiquark pair to dipole is completely lamp derivative and described by a so-called generalized distribution amplitude. However, if we consider ρ0 electron production at the EIC, when Q square is sufficiently large, the whole transition process can be quadratically calculated in terms of a pi distribution amplitude. Now one can make more reliable prediction for the symmetries in vector ρ0 mirror electron production. Okay. So now we come to summary. So there's two messages. Main message I want to deliver in this talk. The linear polarization of coherent photons are firmly established, both experimentally and theoretically. Second, the linear polarized photon beams in UPCs provides as a new experimental tool to explore some level QCD phenomena. It's crucial to take into account two source interference effect in UPCs, and find the coherent photon KT in order for extracting the nuclear geometry information. I think there is also a great potential to explore beyond standard model physics and some strong QED effect with the linear polarized photon beam. Okay, thank you. That's all.
Thank you very much, Jian Zhou, for that very comprehensive discussion of these anisotropies in UPCs. We have time for questions. Does anybody have any questions? I see Spencer. Are you raising your hand?
Yeah. So very nice talk, very thought-provoking. Thank you. I had a question about the Coulomb nuclear interference. So just to clarify, are you talking about interference between photon, and I'll use the word pomeron, photon plus pomeron going to the row versus gamma gamma going to dipions?
Yes, yes, yes.
So, but isn't the gamma gamma to dipions cross section a tiny fraction of that for the row?
Yes, that's true. That's true. But at low transverse momentum, this electromagnetic amplitude is scaled as 1 over t. Mm-hmm. But the QCD amplitude scale the behavior is controlled by the nuclear form factor, which is rather flat at the very low t. So if you go to the sufficient low transverse momentum region, then you will find the place where the electromagnetic amplitude is comparable to the QCD amplitude, just like I showed here. So at a relatively large QT, then all this interference effect will basically dies out. Only at very, very low Q prop, electromagnetic amplitude become large.
Do you have a plot maybe that shows the relative sizes of those two contributions?
Sure. We have this plot in our paper. Yes.
Okay.
We show the relative size of this contribution, yes. Mm-hmm. So,
I mean, can you explain a little bit more what you call elliptical glue? I mean, you didn't explain well when you trying to add another contribution. You call it elliptic glue. What is your?
That's Feng who came after this name. Maybe Feng can answer this question.
What I mean, you can, if I use it, you can explain it. So what is elliptic glue? Is some kind of initial glue distribution with some kind of polarization, or with Fine is not here. Fine is in the office.
Okay. So I guess this because this elliptical glue distribution can cause a cosine to phi asymmetry, and this phenomenon is similar to the V2 flow. So by this analogy, he called this the elliptical glue distribution.
I mean, still, it didn't explain what is elliptic glue. I mean, it caused elliptic flow. I mean, anisotropy, yes, in the final state, right?
Yes. No, it's not elliptical Coulomb. It's called the elliptical Coulomb distribution. It's this distribution.
It is distribution. Yeah. What is?
Because this correlation can produce a cosine to phi as a mass asymmetry. So it's by in related to the V2 flow phenomenon. So I guess this three guys called this distribution as.
Okay.
Okay.
This is sort of what is delta is some kind of impact parameter.
Yes, data purple is a conjugate impact parameter. Yes, it's a correlation between the Q purple and the B purple. So it's a correlation between gluon's transverse momentum and gluon's impact parameter. So it's quite a non-trivial gluon regular distribution because it has a low counterpart, low GPT, low TMD counterpart. By integrating out the Q purple, either Q purple or B purple, then its whole structure vanish.
And this Gluon GTMD must already be existing, right, in the standard classification of Gluon GTMD, right? People already have
Yes.
one.
Not sure.
Yeah.
Probably, unless probably it's not a leading power distribution. So in the classic, in the conventional classification of the GTMD, it may not show up because people only take into account the leading power GTMD distributions, right?
That's true. That's true. Okay. Yeah, I also got a question. So if you look at the next cosine 4, 5 in the very last part, and you said the sign reverse, right, from EIC to star, what actually changed? Like
because there's no double slit interference effect. It's purely caused by the interference effect.
Oh,
at the EIC, you only have one incoming nuclei target.
Oh, okay. Yeah, that's right. Yeah, okay.
Great. Do we have further questions?
Maybe I ask one more. Yeah, so in all this kind of calculation, right? Yeah, it's kind of following earlier question by Farid. So you in your Feynman diagram, let's say low meson production, you have like a 2 gluon exchange, right? And then you do the calculation based on those kind of picture. But on the other hand, I suppose the scale associated with this must be very small, right? So
yes.
do you really have like a gluon degree of freedom or not? Or it's like some kind of and it's not necessarily gluon, right? Because
I have to admit that the perturbative calculation is not well justified for root zero production case. So you have to use some model input.
I see. Okay.
So I have some follow-up questions. It's actually about the raw production. So considering one can get away with the calculation even though there is non-perturbative contribution, there were some results from a star in which they look at the correlations of the pions, of the raw decaying into pions. In your talk, you have showed us correlations for leptons from the J side decay. But have you tried to also compare the raw decay to pions with the formula?
Yes. Actually, I didn't show plots for the symmetry in gypside production, but yes, we also compute the cosine to phi asymmetry for diffractive gypside production. The symmetry for gypside production is quite different from
right. So for raw decaying to pions, the asymmetry, for example, changes sign, right? It has the V2 as the opposite sign. But have you tried to compare with the data? Can you describe the data? Because
the data, we do not have the data for the symmetry in gypside production.
Not for gypside, but there is data for raw decaying to pions, right?
Yes, so we compared this.
Oh, sorry. Yes. This is the raw precise. Okay. And so here, do you include any soft photon radiation? Because in principle, these charged pions can also.
We here we didn't because this log is not so large for zero production case, so the QED correction is negligible. So there is a zero mass and there is a pi mass, so it's not actually not a large log. But for chip size case, we have to include the QT correction.
So for J psi production, I guess one, maybe this is a very naive question, so apologies to the audience. So the J psi can decay to electron and positron, but it can also decay into muons, right? Is that correct?
Yes.
So if you look at the muon channel, then
yes.
You can reduce significantly these final state effects, right?
Yes.
Okay.
Yes.
I think it maybe it's, I don't know experimentally if it's feasible, how difficult it is one versus the other, but I think it could be another handle to understand understand these kind of effects. Yeah. So I have a few more technical questions, but maybe I let. Does anybody have any further questions from Jian Zhou?
Maybe you guys discuss in private.
Yes, sounds good. So let's formally close the seminar, and thank you very much again for this nice presentation.
Okay. Thank you for the invitation again. Okay. Very nice. Thank you.
I'm gonna stop recording now.